All right, here's SIG number 2, which is all about limits. And something you're going to learn on Monday is you're going to need for this, and actually makes your life a lot easier. But just know that if you're watching this before Monday, January 20 something, then you might be confused on this. All right, so the idea for limits is there's a thought process we need to go to, right? A limit tells us what happens as we get really close to an x value. What happens to the y value as we get really close to an x value, right? So example, in this first one is saying what happens to my y value as x get really close to -3. And before calculus and pre-calculus, usually it was just like if you had a function like this and you're plugging in 3, then usually the y value could just be determined by f of 3. You just plug it in and get the value, right? So that's the first thing you want to try, is always try direct sub first, right? Now, depending on what you get with direct sub, if you get a number like 3, then you're done. Then this is the answer, right? Then you're done. Then 3 is your answer. If you get a number like, say, 5/0, then your answer is either positive or negative infinity, which means the limit does not exist. And then the case where you have to do a lot more work is if you get 0/0, which is indeterminate form. Then that means you have to do something else. That something else means you can use this thing called L'Hopital, or you can factor, or you can rationalize if you have like square roots. Simplify. This is for like fractions, or trig, or anything else. And that's basically how that goes. All right. This is for limits that are not going to infinity, right? So let's try our first one here. The limit of x goes to -3. The first thing we should do is do direct substitution, which if I plug in -3, I'm going to get -3 plus 3 over 9 minus 12 plus 3, which this is 0/0. So that tells me that I didn't get a number. I didn't get a number over 0. I got 0/0, indeterminate form. I need to do something else. This one should be the type where you factor. So we're going to say it is important you keep writing this limit notation. Otherwise, you would technically get it wrong. Factor this. It's going to be x plus 3, x plus 1. These two will cancel, and you'll be left with what we say is this is a function that agrees with the original at all but one point. The only point it doesn't agree with it at is at x equals -3. So now I plug in -3 and I get 1/-2, and that is the answer. That's the limit. Or if I plug in -3, 1/-3 plus 1. All right, so that's that. The next one you have to be careful on. This one's asking what happens as r approaches 2 from the left. Now it might not always say this. It might say r approaches 2. If it says r approaches just flat out 2, I need to check the left and the right to make sure they're the same. If it said from the right, then I could only check the right, but since it says the left, I need to check the left only. So we're trying to think, well, what's left of 2? Is it r less than 2 or r greater than 2? Turns out it's less than 2, so we're just going to try direct substitution, which means it's going to be 2 times 2 minus 5, which is 4 minus 5, -1. And that's the answer, right? If you can just plug it in and get an answer, that's your answer. All right, so here we go. Number 3. Again, we should be trying direct substitution, showing what we get. In this case, we get 0/0. Let's draw an arrow because it doesn't actually equal that. It's just going to 0/0. So that tells us indeterminate form, we need to do something else. What that something else could be is either L'Hopital or rationalizing. Let's give L'Hopital a shot, right? So what L'Hopital says is if I do direct substitution and I get 0/0, then what I can do is I can do the same derivative, but this time I can do f prime over g prime. Right, so basically you can just take the derivative of the top and the derivative of the bottom and then try to evaluate the limit, right? So what we're going to do is we're going to keep the same limit, take the derivative of the top, which is 1, take the derivative of the bottom, which, you know, square root of w is w to the 1/2. So it's going to be 1/2 w to the negative 1/2. The 1 goes away. And then let's go ahead and just rewrite this. All right, because this is negative in the denominator, it's going to come up to the numerator, so it's going to be w to the 1/2. And then this 1/2, it's like 1 divided by 1/2, which turns into like 2. So it ends up being like this. There's other ways you can do this too, but I think this is the simplest way. And then w to the 1/2 is the square root of w. So now we're going to plug in 1, and we're going to get 2 times the square root of 1, which is 2. So it turns out this limit is 2. Okay, number 4 is asking us to find the limit as x goes to -3. So we need to find -3, which is here. This is a graph, and we just look down and see, well, what's the y value? If I can just see it directly, what's the y value when x is -3? Well, it turns out in this case, it's also -3. This, you know, these won't always be this easy. Sometimes you'll have like asymptotes or jumps or whatever right there as well. All right, next one is this, the limit of this whole sine function thing here, which looks really complicated. The idea here is that you can recognize this as something we learned in the first semester, which is f of x plus h minus f of x over h, which it's similar except it has like this x on the bottom, which is the h, because this is going to x is going to 0 instead of h going to 0. And this was the definition of a derivative, right? This is the definition of f prime. So one thing to recognize is, well, where's f of x in this? F of x is this term over here, so that's this, right? It's telling us that's the thing we want to take the derivative of. So it's saying f of x is sine x, not pi over 6, right? Because they're actually trying to find the derivative at a point, just sine of x. F prime of x would therefore be cosine of x. And then we're trying to find f prime of 0. No, sorry, f prime of, this is where we're trying to find the derivative as, pi over 6, would give us cosine pi over 6, which cosine of pi over 6 is pi over 6 here. Cosine is the longer one, so root 3 over 2. All right, that's one way to do it. Let's just briefly do another way to do it. Another way to do it would be to plug in 0. You're going to get sine of pi over 6 minus sine of pi over 6. That's 0. And then over 0, so you can get indeterminate form. So you can use L'Hopital's rule. So we take the derivative of the top. Derivative of sine is cosine pi over 6 plus x. The derivative of sine pi over 6 is just 0 because it's a constant, and then derivative of x is 1. And then we're taking the limit as x goes to 0, so we're going to plug in 0 there, so it just turns into cosine of pi over 6 again, which gives us that same answer. Right, so either way works. Next one, the limit of this function as w goes to -infinity, right? So we're going to -infinity. We're going that direction. What happens to this as I go that direction? Well, it's getting, in this case, you can see that it looks like it's getting really close to this line here, which is the line y equals 1. So this is, as w goes to -infinity, this is approaching 1, right? The y value is approaching 1. You can kind of also evaluate this algebraically, right? E to the 1 over w, the limit as w goes to -infinity. If you just like kind of try like a direct substitution, it's 1 over -infinity, which is like e to the 1 over negative infinity is effectively 0, right? 1 divided by a really, really big negative number, doing your calculator, right? 1 divided by 10 billion. It's going to give you something really close to 0. And e to the 0 is 1, right? So as you get really close to negative infinity, it's going to get really close to 1. All right, number 7. Is the limit of this as w goes to infinity. Basically, you're going to try to plug in infinity, right? You're going to, or plug in negative infinity in this case. You're going to get negative infinity to the 4th power. Actually, let's not do that. It's going to confuse some people. Like, the idea is, what happens is w gets really, really big, right? And so all that ends up really mattering is the leading term, right? None of these other terms are going to matter because not the leading, but the highest degree term, right? So w to the 4th is going to dominate all of those because as w gets really big, that's going to be the biggest of them all, and the other ones will become insignificant. So we're just asking, as w goes to negative infinity, what happens to w to the 4th power? Well, w to the 4th power, you know, is always going to be positive, and then if it gets really big, it's going to get really big as well. So this is going to go to positive infinity, right? Be careful if it was odd, right? If this were odd, it would go to negative infinity because odd powers give us negative numbers. So this one goes to infinity. Be ready here for, you know, rational functions too, like if you had something over something and if they use an in-behavior model, that kind of stuff. Just be ready for that. Next one is determine if each function is continuous. If it is not continuous, find the x-axis location and classify each continuity, right? So in this case, we have g of r equals negative r plus 4. This is a polynomial, which means that polynomials are always continuous. So this one is continuous over its entire domain. Next one is evaluate each limit, use L'Hopital. So this one we're forced to use L'Hopital if it can be applied. If it can't, we want to use another method and write a star next to your answer. So how do I know if L'Hopital can be used, right? So it has to be an indeterminate form. So indeterminate form is 0 over 0, or in some cases you might get infinity over infinity, right? So if I plug in infinity, I'm going to get natural log basically infinity to the 3rd, which is infinity, over natural log infinity again. Now these are not the same levels of infinity, right? Because x to the 3rd does not give me the same thing as x to the 4th. So this is infinity over infinity. Let's write an arrow again because it's not equal to that, which is indeterminate form, right? You can't cancel these out and get 1, right? Just be wary of that because they're different levels of infinity. One of them is bigger than the other one. One way to kind of view this would be to kind of look at the bottom and notice that, you know, the bottom is larger, so it's growing faster. So this thing should, you know, it's kind of like small over big, where it should be tempted to think it goes to 0. But since we got indeterminate form, we're going to go ahead and take the derivative of the top and the bottom, right? So we're going to take the derivative of this, which is going to give, that's u prime over u. Derivative of natural log is u prime over u, so it's going to be 3x squared over x cubed divided by derivative of this, also u prime over u. It's going to be 4x plus 1 to the 3rd over x plus 1 to the 4th. And we need to clean this up. We're still doing the limit as x goes to infinity. Clean this up. The top one's going to be 3 over x. The bottom one is going to be 3 of these. 3 of these x plus 1s will cancel 3 of those, and you'll be left with 1 down here. So it's going to be 4 over x plus 1. Since instead of dividing these two fractions, we can multiply by the reciprocal. So it's going to be 3 over x times x plus 1 over 4, which is going to give us 3x plus 1 over 4x, and we're still doing the limit as x goes to infinity, right? And now we can see that if you do like an in-behavior model, you can see it's going to be 3x over 4x, the terms with the highest degree on the top and the bottom, and the x's will cancel, so we'll have the limit as x goes to infinity of 3x over 4x, and these x's can just cancel each other out, right? X over x is just 1, and so this goes to 3/4, and that's our answer, 3/4. So that's really not obvious from here. We're saying it should go to 0, but I guess they grow pretty proportionally to each other. All right, I hope this is helpful. There will be different types on here, right? So be ready, look at some of the other examples and stuff from previous lessons, and hopefully that'll help.